let me kind of remind you that in these problems, I gave you a set of steps. And those steps are not absolutes. I mean, I don't have every little thing delineated there, but I certainly have quite a bit there, don't I? And it can be intimidating. So let's just boil it down. There are 4 things you have to do. Step 1, you need to decide if you can, is it a first law or second law problem? Trying to get you to understand that we are making choices here. And we're trying to observe what's happening in the problem. I haven't talked about what this problem is yet. I'm just saying these are the steps that we have to do. And then step 2, I can boil it down. It's a free body diagram with a coordinate system. But you and I both know this is the one that takes up all the paper, right? I mean, this thing starts off and goes all the way down one side of the page and halfway through the other page because there's a lot that has to be done here. This is the part where you draw a picture and you ask what kinds of forces are acting. So, the picture's involved and you're drawing arrows. You're going to talk about whether there's any fundamental forces, any clear pushes or pulls, and then any resistive forces. That's kind of how they're broken down. If you read it and you looked at it, you saw that they're broken down kind of like that. There are other names in there, but that's really what it is. And then the coordinate system, well, that's for you. That's to help you. Step 3 is to actually apply your chosen law. That means breaking it up into components, but also making sure that you know that some of the forces are going to work in one direction and some of the forces are going to work in the other because your math only allows for one-dimensional work. And step 4 is the one is probably the most ambiguous. You want to, analyze. Draw a conclusion. And perhaps, find a solution. The best way to put this is that it's here where you will answer the question. This is basically what it comes down to. And I'm telling you, it's super simple when you're watching me do them. So let's consider the car. I tried to make it look as though the car is moving to the right. So that's kind of what I'm drawing there. So we have a car that is moving to the right. And let's say that the car has an acceleration of 1.5 meters per second squared and a mass of 1,200 kilograms. And let's say that the engine of the car is pushing the car forwards with 2,000 newtons of force. Again, let's say that the engine of the car is pushing the car forwards with 2,000 newtons of force. Have we got the basics down? I'm going to ask 2 questions. What resistive force is acting on the car? And what's the net force acting on the car? Okay? Got the basics down? All right. All these problems start in the same place. Step 1. Is this going to be a first law problem or a second law problem? Second law problem. This is a second law problem. The net force equals ma. That's right. We know that because there's a clear acceleration given to us. That's what makes this a second law problem. All right, we've completed step 1. Step 2 is to come up with a free body diagram that could be used to help us solve the problem. A free body diagram begins by making any mass for each object a point. So I'm taking the entire mass of the car and reducing it down to a point. We're going to draw arrows on this point, and those arrows are drawn from the center of the object, or from the point, away from the object. Those arrows represent the forces that could be acting on the car. We're going to go through a series of forces that we know about to see which forces or which arrows we draw. So let's start at the top. Are there any fundamental forces acting on the car? Go ahead.
Gravity.
Yes, gravity is acting on the car. So we draw a downwards arrow to indicate the force of gravity. Now, since this is a force that's very likely to be in almost every problem, we kind of use this arrow to make a judgment call about the size of the rest of the arrows we're going to draw. So we know the size of this arrow. It's weight, and weight is mg, the mass of the object times the acceleration of gravity. Look, the mass is 1,200 kilograms. The acceleration is 10, so that's got to be about something that's 12,000 units long. We're going to draw other arrows, but we kind of have a starting place for how big the arrow should be. So we go on to the next one. Is the car being pulled on by any ropes or cables? Do we see any that are there? Nope. So I'm going to leave that one out. There's no tension force acting on the car. Is the car in contact with any surface? Yes, the ground. So there must be a normal force acting on the car. By definition, normal forces aren't ordinary. Normal means perpendicular. So normal forces are perpendicular to the surface in contact. So I'm going to draw an upwards arrow because that's perpendicular to the ground. I'm going to label it N for normal. Now, are there any other forces that we need to deal with? Yeah.
The force of the car.
Yeah, we were given a force. That's going to happen where a force is just given to you that you must use. In this case, it was the force of the engine. So what direction do we think the engine is pushing on the car? Yeah, we're not trying to make it hard. It's probably pushing on the car to the right. And how big should this arrow be? Should it be bigger than the weight or less than the weight or the same size as the weight? Less. How big is this arrow? How much force is the engine applying to the car? 2,000. I don't have another name for it. If you want a name for it, you can call it like the applied force or something like that. Now, are there any other forces acting on the car? Yeah. Well, there's got to be something because we're being asked about a resistive force. It's plausible that the list that you have isn't an exhaustive list. There could be other forces. I would say that a resistive force is probably a combination of air resistance and friction and stuff that acts on the car. Makes reasonable sense, right? We're not trying to fool you there. There'll be other places. This is not it. Now, I need to draw an arrow to represent the resistive force. What direction should I draw that arrow? Do you think the resistive force is in the direction the car is going or against the direction the car is going? I think it's against the direction the car is going. But I also think it should be less than the force of the engine because the car is accelerating. So I think the forces should be unbalanced. And that should be clear. Every force needs a label or else it doesn't count. All right, we have identified all the forces that are acting on the car. It's now our responsibility to try and take this and break it up in such a way that we can solve it, which means applying a coordinate system. Now, truthfully, this is the end of the line for drawing a free body diagram. Everything we're doing now is an attempt for us to solve the problem. Now, solving the problem means taking this and making it in such a way that we can handle it. So when we apply a coordinate system, I gave you two priorities because you could draw any coordinate system you want, but you want to make this something that you can solve. So the highest priority is to always draw the coordinate system in the direction of the acceleration. If it's not accelerating or if that's not possible, your next priority is to try and line the coordinate system up with as many forces as possible. But we know the car is accelerating, and we know it's accelerating to the right, so we're going to draw a coordinate system that is aligned with the direction of the acceleration. We're going to make that direction positive on purpose. And after that, we have to draw the y direction perpendicular to the x direction. There, we have drawn a coordinate system that will help us solve our problem. It is aligned with the acceleration. Do we have any forces that are not along one of the directions? If there aren't any, then we don't have to worry about breaking up off-axis forces. So we can start right here solving our problem, which means we go to step 3, apply Newton's laws. So we have a law for Newton to use here. We said it was a second law problem, so we're going to break this up into the net force in the x direction and the net force in the y direction. Which one of these gets ma and which one doesn't? Which direction do we line up with the acceleration? X, so that one becomes ma, and that forces the other one to be 0. If done correctly, your acceleration should only be in one direction. All right, applying Newton's laws means that you follow the set of instructions that are there. These were instructions that said add up all the forces in the x direction and set them equal to ma. So I'm just looking, I see two forces that are in the x direction. Do you? 2,000, that's in the positive direction, so 2,000. Fr, that's in the negative direction, so minus Fr. And I'm told, once I've gotten all the forces that are in the x direction, set that equal to ma. Done. I followed the instructions. Moving on. Add up all the forces in the y direction, set them equal to 0. I see two forces in the y direction. I see normal force in the positive y direction, normal. And I see weight in the negative y direction, so negative weight equals 0. That's it. That's what Newton's laws do. They generate relationships. And it has generated for us two relationships. Maybe we can solve our problem with them, maybe we can't. But that's what Newton's laws do. Now, there's other things you're going to need to know how to do, and I put that on the sheet. Like, recognize that there are substitutions for weight. Right? There's something you can plug in there that you can use for weight. It's on the sheet, use it. It's mg. Also, we were asked to figure out the resistive force. That means solving for this. I think I can do that. You guys seeing what I'm talking about? So I'm going to take 2,000 minus the resistive force equals the mass of the car, 1,200. The acceleration of the car was 1.5. Here we go. I see a way to get to the answer to the question. You guys following along? Let me say that. We'll see. Now, you know that I really don't care about the number answer, but I know you guys do. So punch all your buttons and all, and make yourself feel better and find that the answer is 200. Now, are we all good, or I have to wait for you guys to do that? All right, so those are our basics. We're pulling on the wagon by pulling on its handle with 20 newtons of force, angle 30 degrees, and the wagon has a mass of 5 kilograms. The wagon rolls to the right at a constant 2 meters per second. What is the size of the frictional force and normal force acting on the wagon? I don't know if you can do all of that, but you should be able to do step 1 and step 2. Let's start with step 1. Is this a first law problem or a second law problem? I knew I'd get you. It's not a second law problem. Because it says right away, has to be accelerating. Is a thing accelerating? Nope, so net force equals 0. Motion doesn't mean acceleration. All right, we got our first law down. You guys draw me that free body. We need to make a free body diagram, and a free body diagram begins with a dot representing the mass, representing the mass of the object. Our object is the wagon. We ready to begin? All right. Are there any fundamental forces acting on the wagon? Gravity. So I will draw an arrow representing gravity. How do I draw that arrow? Downwards. So I will draw an arrow that is straight down, or not. Let's try again. I know quite a bit about this arrow because the wagon's 5 kilograms, making this 50 newtons, but I'm just going to write a big W there for the weight of the wagon. Let's go on. Is there anything pulling on the wagon? Any cords, cables, handles? Yes. So that force must be drawn so that it is in the direction of the cord, cable, or rope, which means at an angle, 30 degrees. So all of you drew something straight to the side. Can't. It's got to be at the angle it was given at. Is the wagon in contact with any surface? Yes. So there must be a normal force. Normal forces are perpendicular to the surface in contact. So I need a force that is directed upwards. And when I draw that arrow, I'm going to purposely draw it less than the size of the weight. The handle is pulling upwards on the wagon already. So the floor doesn't support it so much. Or at least it supports it less. I mean, come on, anybody stand on a scale before and then lean on the counter in the bathroom to see the number change? I think we've all done that. That's what you're doing here. The scale tells you your normal force. Do you think your weight actually changed? Now, does this look balanced to you? Now, we know it has to be balanced because it's a net force equals 0 problem. But that picture doesn't look balanced. For every up or down, for every left or right, I see forces to the right, I see no forces to the left. What is the likely force in the wagon to the left? Go ahead. Friction. So we're going to write friction. So I think I'm going to try and make it so it's about the same length as this is in this direction. I'm going to label it friction. This is a free body diagram. Now we're going to try and use this diagram to answer some questions. So we want the normal force and the frictional force. Those are the questions, but we're still going to continue to proceed with our set of steps. So the next step is for us to apply a coordinate system. And our highest priority is to apply that coordinate system in the direction of the acceleration. Is this object accelerating? No. So our next priority is to try and line it up with the most forces possible. So would it make sense for me to choose a coordinate system lined up like this? That would be lined up with one force, but remember, I would also have to put the y direction perpendicular to that, and that seems to me like it's only lined up with one force and not lined up with 3 of them. That seems like a bad idea. Now I will see, and I will put this one on the board for all of us to see, the person who will draw their coordinate system like this. Somebody in the room will do this. Is that okay? No. But when you do, just note, I'm going to hang it up on the board for us all to see. Just so you know, I may or may not have your name on it. I probably won't because that would be shockingly mean to do. But it depends on my mood that day. And we all know I can be moody. So, but I'm also trying to really throw it out there. Do you understand why that would be wrong? X and Y have to be perpendicular to each other. They have to be. Are those two things perpendicular to each other, those white lines? Oh. So I'm going to make the X direction this way. And I understand that one of those doesn't line up. That's okay. I'm going to make the Y direction this way. And again, luckily both of those are pretty good. But I'm going to make this the positive X direction, and this the positive Y direction, this the negative X direction, and this the negative Y direction. Now, guys, look, your notes need to do something for you. So right now, write some notes down. I know you think you know why I did all these things, but when we're all done, you won't remember. Why did we do this? Why did I draw it like that? Which priority did I use? Because it looks a lot like the last question. But we chose these for a different priority. It was lined up with 3 of the forces. Unfortunately, one of these forces is off axis. Do you see that? We have to deal with any off axis forces, which means this force, which is at 30 degrees and is 20 newtons, is off axis. I need to break it up into its components. So for right now, I'm going to ignore everything else and just focus on this one arrow so I can break it up into components. I'm going to separate it into 2 arrows that will take the place of 1 arrow. Now, for you guys who don't remember, we just did this in our last test. We took any of the vectors that were not in the cardinal direction and broke them up into how much in the X direction and how much in the Y direction. So that's what I'm going to do here. I'm going to consider that this particular arrow has a certain amount that's in the X direction and a certain amount that's in the Y direction. Right, that's what we're doing here. We know that this is 20 units long. It's 20 newtons. This is the opposite side. This is the adjacent side. So this side's going to be 20 sine 30. And this side's going to be 20 cosine 30. And no, I don't want to write out sine theta equals opposite over hypotenuse every time. We're kind of past that, I hope. And if you're not past that, yes, it will take you longer. But here's the thing to remember. When I separate that vector into its components, what I'm really doing is I'm saying that I no longer need that information. And all I really need is take this and place it over there, and those 2 vectors now replace what was there before. Except they're really tiny and are hard to see. But they take over for the vector that was there before. Now, what I have here is no longer a free body diagram because I've taken one of the forces and broken it up into components. So when you have a free body diagram and you're asked to produce it on the test, you can't put the components on it. You have to do that somewhere else on your paper. There will be a box on your test that says put the free body diagram in here, and it will be the one that doesn't have components on it. But will you notice that all of the forces now are lined up with the X direction or the Y direction? Which allows us to go to the next step and say net force in the X direction and net force in the Y direction. Was this a first law problem or a second law problem? First, which means both of these are 0. So now we just go and anything pointing up, put it in the Y. Anything pointing down, put it in the Y. Anything pointing right, put it in the X. Anything pointing left, put it in the X. And assign direction. So I got 20 cosine 30. 20 cosine 30. Got that? Friction. It's in the negative direction. Minus friction. That equals 0. All right, moving on to the next one. I have normal. Pointing upwards, it's positive. I have 20 sine 30, pointing upwards, so it's positive. And I have W, pointing downwards, so it's negative. That equals 0. Now your job, if you'll remember, was to find the size of the frictional force and the size of the weight. Can you do that with what you have now? I hope so. I don't think we have to go that step, right? You guys can do that on your own. We can try a different question now. Good, we're going to try a different question now. So, let me see. So, again, you're pushing on the book with 20 newtons of force at an angle of 45 degrees with the vertical. The book has a mass of 1.5 kilograms, and it's sliding upwards at half a meter per second. What do you think? Friction? Tell me what the frictional force is. Tell me what the normal force is. Seems like appropriate things. Can you start by drawing a free body diagram that would kind of help us solve this problem? But before you do, is this a first law problem or a second law problem? First law problem. Somebody said second over here. But it's first. Constant speed, 0.5 meters per second. All right, draw a free body diagram first. Gravity. So gravity is a fundamental force acting on the object. How do I draw that arrow? Downwards arrow that is 15 units long. All right. Are there any contact forces in this problem? Any cables on that book? No. All right, so no tension forces. Is it in contact with the surface? Yes. So how do I draw that force? What's that? Normal force, some of these we don't get choices. In the normal force, we don't get a choice. It has to be perpendicular to the surface. So if that wall is vertical, then I have to draw an arrow to the left that is perpendicular to the wall. And it's, I don't know how big to make it, really. It's 20 Newton, it's got to balance at 20 Newton force, but it's at an angle, so I'm just going to draw it kind of like this. I don't know, something like that. Now, you're right. We are going to have to deal with that 20 Newton force. That's a force that's given to us, so we have to use it. There's not really many choices to make, but how did you draw it? The arrow has to start at the dot and be drawn away. So you can't draw something like, that looks like this. That won't work. So for this case, you just kind of pass it through and put it over there. So that's what we're going to do. We're going to draw an arrow. Sorry to bore you. It's passed through, and it's got to be the longest arrow that we've drawn here, because it's the one that's 20 newtons, and the weight of the book is only 15 newtons. Now, are there any other forces acting in this system? I don't know. I think there might be, yeah. There should be friction. I asked you, what is the size of the frictional force? Likely there's going to be one. What direction do you think friction acts? What's that? The book is sliding up. And friction is a force that opposes motion. So it's got to be down. That's right. So how you draw this is up to you. I'll give you some choices. This is weight. This is normal. But friction, you can either draw it like a stacked arrow like this. This is one way to do it. I'm not a fan of this way, but it doesn't make any difference whether I'm a fan or not. This is what some people like because they like the way that looks. I generally draw two forces in the same direction. I just draw them side by side. But you can pick what you want to do there. It makes no difference. I think we've identified all the forces that are acting in the system. We now have to apply a coordinate system. Is this object accelerating? No, so our coordinate system can be lined up with as many forces as possible. I see 3 forces that are all kind of lined up already, right? Friction, weight, and normal are all in the X or Y direction. So I say we use them. So I'm going to draw a coordinate system that is lined up with the horizontal and the vertical. There we go. And we're going to have to deal with the angle here. Luckily, it's 45 degrees. So when it's 45 degrees, Even if you screw it up, you'll probably still get the right answer. But you know that that's not going to be okay, right? So where do you think the 45 should go? Should it go in choice number 1 or choice number 2? I'm hearing a couple ones. It's 45, so it won't matter. But if it were theta and you're judged on where you're going to put it, you understand that's going to be a problem, right? So I'm going to help you with this one. Let's draw that line there. That's lined up with the arrow, right? And let's draw another line here. That's lined up with the vertical. What are these two angles here and here called? Come on, geometry freshmen. There are vertical angles. That's right. And vertical angles are congruent. So I have to put that 45 degrees in the place that will be congruent, which will be where 2 was. 45 degrees is there. Let's not get those wrong. Because if it were 30 degrees, that would screw up all of your work, right? All right. The next part is still the next thing we do, right? We have an off-axis force. So we have to take that off-axis force and break it up into components. That means triangle work again. So I'm going to grab a arrow and draw it this way. One that's drawn along the vertical first. I'm trying to wrap a triangle, a right triangle, around the angle there. So I think that'll do. And let's see, this is going to be 20 cosine 45. This one will be 20 sine 45. And once we've done that, we no longer need the original one that was there. It was just there long enough to get us our components. Boom. Now we have a whole bunch of one-dimensional forces. So we're going to solve our problem now. We're going to take and write net force in the x direction, net force in the y direction. They both equal 0 because this is a first law problem. In the x direction, it looks like to the right, I've got 20 sine 45, so got rid of him. And to the left, I've got normal, so got rid of him. And that's it, right? In the x direction, those are the only ones that are lined up in the x direction, so I set that equal to 0. All right, in the y direction, it looks like I've got 3 of them, right? I've got that 20 cosine 40 degrees. 45 degrees. So it took care of that. But then I've got friction downwards, took care of that. And weight downwards, took care of that, set that equal to 0. That's all of them. I wouldn't really have to cross them out, but I'm doing it to show you that you just have to take each of the things that's pointing in one of those directions and line them up. Could you now figure out normal force and friction? You probably have to do some substitution, right? You probably have to substitute in mg for weight to do that. This one you wouldn't. You could solve it right now. All right, you guys are seeing what you're going to have to do tomorrow. It's easy when Mr. Shelton does them. Yeah. What's that? Well, if we look at this one, we want the frictional force. So we'd get 20 cosine 45 minus friction minus mg equals 0. Well, m is 1.5 kilograms for the book, and g is 10 meters per second squared for the acceleration of gravity. What's that?
I have a question. Do you have